Hi, and welcome back to my videos for Physical Chemistry 1. For the past several videos, we've been looking at how the entropy is connected to simple parameters of a system, like the pressure, temperature, volume, and the moles of the compounds in the system. In the last video, we looked at the entropy change that takes place when the phase of a system changes, and we saw that for a phase change, the entropy is connected to those other parameters of a system using the Clapeyron equation. We also saw that for systems undergoing vaporization, the entropy can be described using the Clausius-Clapeyron equation, and by this equation, which is derived from it. It turns out that lots of practical chemical experiments depend on phase changes. For example, distillation involves transitions between the liquid and vapor phases, and crystallization depends on liquid to solid phase transitions. For this reason, it's worth delving deeper into the thermodynamic changes that happen when a system changes from one phase to another. It turns out we can summarize how the temperature and pressure can change the phase of a substance using what's called a phase diagram. A phase diagram is just a graph with the pressure on one axis and the temperature on the other. We draw lines showing the areas where the compound can be a solid, a liquid, or a gas. So, for example, suppose this pressure is 1 atmosphere, and we start at a low temperature where the substance is a solid. If we raise the temperature but don't change the pressure, that means we go to the right on this graph. Eventually, we hit the dividing line, and when that happens, the substance becomes a liquid, so that's the melting point. Remember, when this happens, we're performing a kind of reaction, and the phase change has an enthalpy. As we saw before, if this substance were cesium, changing it from a solid to a liquid would take 2.09 kilojoules per mole. Notice that if we were lowering the temperature, we'd be freezing the substance instead of melting it, and the enthalpy would have the opposite sign. If it were cesium, the enthalpy change would now be negative 2.09 kilojoules per mole. Also notice that if the pressure were higher or lower, the melting point would be different. For example, if we were at 2 atmospheres, you can see that the melting point for this substance would be higher. There are two other things to notice about phase diagrams. First, there's always one point on the graph where the solid, liquid, and gas phases all meet. If the pressure and temperature are exactly the ones at that point, then all three phases will exist at the same time. For example, you know that at 0 degrees Celsius, you can have liquid water and solid water in the same glass. That's just ice water. But you don't have water vapor in that case. However, if you got the pressure and temperature just right, you could have all three phases. That spot on the phase diagram is called the triple point. Also, notice that the line separating the liquid and gas phases stops at a very high pressure and temperature. That's because if we get the pressure high enough, a gas becomes so thick that it's not possible to distinguish between a gas and a liquid anymore. They become basically identical. The place where that happens is called the critical point, and the temperature and pressure at that point are called the critical temperature and the critical pressure. One important concept that will help us tie phase diagrams to the work we did with phases in previous videos is called the phase rule. The phase rule is a simple equation derived by Josiah Gibbs, and it describes the behavior of the phases in a system at equilibrium. The phase rule tells us how many different parameters of a system, like the pressure, volume, temperature, and the number of moles of each component, can be varied without changing the number of phases present. The equation itself is deceptively simple looking. In this equation, C is the number of components, P is the number of phases, and F is the number of degrees of freedom. Let's look at each of those more carefully. First, let's look at P, the number of phases. This actually isn't always as simple as it seems. For a system consisting of just one compound, P is easy to determine. For example, here's a phase diagram for water. If our temperature and pressure are such that the system is located at this point, or this one, there's only one phase present. the system is a solid, liquid, or gas, and that's all, so P equals 1. If the temperature or pressure are such that the system is located along one of the boundary lines, there will be two phases present, so P will be equal to 2. For example, at this point, both the solid and liquid phases will be in equilibrium. And there's one point, the triple point over here, where all three phases will be in equilibrium, so P will be equal to 3. However, the situation is much less obvious if there's more than one compound present in the system. For example, suppose our system consists of two compounds, water and carbon tetrachloride. Both of these compounds are liquids at standard temperature and pressure, and at first it might seem that P would be equal to 1. However, carbon tetrachloride is a nonpolar molecule, and water is highly polar. Therefore, the two compounds form an immiscible liquid. The two liquids separate so that the two different liquid phases are present. For that reason, P equals 2, even though both compounds are liquid. On the other hand, if we combine ethanol and water, the two liquids do form a miscible liquid. In that case, P is equal to 1. A similar situation can arise with a combination of two solids. For example, if our system consists of a combination of solid zinc and solid copper filings, the two components are easy to see and separate, and P is equal to 2. However, if we were to melt the two metals together and thoroughly mix them, then allow the system to cool again, the resulting product would be a sample of solid brass. In this case, the copper and zinc have become indistinguishable from one another, so there's only one phase, and P equals 1. Finally, let's think about what happens when we combine a solid and a liquid. Suppose we add a sample of calcium carbonate to water. Calcium carbonate is an insoluble compound, so the resulting system consists of water with solid calcium carbonate at the bottom of the beaker. In that case, two phases are present. However, if our system consists of sodium chloride and water, the sodium chloride will dissolve and be indistinguishable from the liquid, so there's only one phase, and P equals 1. But note that this won't be true anymore if we add so much sodium chloride that the solution becomes saturated. In that case, there will now be some undissolved sodium chloride in the beaker, so a second phase is present, and P equals 2. Next, let's look at the variable C in the phase rule equation, the number of components. Suppose we have a system consisting of ice and water in equilibrium. In this case, two phases are present, so P equals 2, but there's only one component because both phases are made of the same compound, so C equals 1. On the other hand, if we have a solution of salt and water, there's only one phase because the salt is soluble, so P equals 1. However, there are two components because the salt and water are different compounds, so C equals 2. The last variable in the phase rule is F, the number of degrees of freedom. This describes the number of parameters of the system that can be varied while still allowing the system to be at equilibrium. The parameters we're talking about here are usually properties like the pressure, volume, temperature, and the number of moles of each component. For example, suppose we have a system of ice and water at equilibrium. In that case, there are two phases and one component, so P equals 2 and C equals 1. Using those values in the phase rule, we find out that F is equal to 1. That means there's only 1 degree of freedom. What does that really mean? It means that we can choose one parameter and set it equal to whatever value we wish. But if we want the system to still be at equilibrium, the values of the other parameters will only be able to have one particular value. So, in the case of our ice-water solution, we can choose one parameter and set it to any value. For example, we could choose to set the temperature to -10 degrees Celsius. However, if we do that, there's only one pressure that will still allow us to remain at equilibrium. In this case, the pressure will need to be about 1100 atmospheres. So, if we change the temperature of this system, we have no choice about the other parameters of the system if we want the two phases to still be in equilibrium. Alternately, we could choose to set the pressure at a particular value, but in that case, we'd have no choice about the necessary temperature. That's what we mean by there being only 1 degree of freedom. For another example, suppose we have a system consisting of salt and water. In that case, P equals 1 and C equals 2, which would mean that F would be equal to 3. In other words, we could choose up to 3 parameters of the system and give them any values we choose, and still retain equilibrium in our system. So, for example, we could choose to hold the system at any temperature, and also choose to have the number of moles of water and salt at any values, as long as we don't saturate the solution. Once we've set those 3 of our parameters, the other parameters will not be freely variable if we want to stay at equilibrium. Well, that's enough new material for now. Soon you'll be having another exam in this course. I hope it goes well for you. When we meet again, we'll start looking at properties of solutions, which will help us understand processes like distillation more deeply. I hope you'll join me for that. But until next time, have a good week.